Lecture 2.4b. In last night's video, we talked about that example with the flies, and we talked about estimating the instantaneous change on day 23. We wanted to know how was the population of flies growing at that particular moment. And one of the things we saw was that it's not possible to calculate it precisely, so we estimate it using a series of slope calculations. Well, in this video, we're actually going to learn how to precisely calculate that instantaneous slope, the rate of change on one day or at one particular moment. Let's start with a quick refresher though. Suppose I did want to estimate. This first example is the function x squared, and they're asking us for the slope of the function x squared at the point 2, 4. Now, asking for the slope of a function is just the abstract version of asking for the rate of change. And they do want the instantaneous rate of change at this point, but we're not going to find the instantaneous rate of change. We're just going to estimate it. The strategy that we'll use, if you think about what your normal parabola looks like, is we have this point right here. And in fact, the point 2, 4, which is a point, not an interval, is essential to our calculation. So make sure that you know that the tangent line really depends on the point. So we have the point, and we're going to start out with a secant line that goes through that point and some other point on the curve. Maybe it looks like this. And I'm going to take that secant line and I'll calculate the slope. But instead of just taking that slope, I'm going to do this again. So after I take my first interval, I'm going to take another interval that's slightly smaller, and I'm going to find the secant line of this next line that goes through a point slightly closer to the point I really care about. And then we're going to repeat that process, maybe once or twice more, with another interval and another secant line, until we start to sense a pattern. And we're going to look at what happens to the slopes, and then we're going to make a guess about the slope of the tangent. Remember visually that a tangent would be a line that just barely grazes the function at this point without crossing through it and only touching at that one point. So go ahead and set up your work. In fact, pause the video and choose some intervals that you would want to use. When you press play, you can see the ones that I chose. Okay, so these are the 3 intervals that I chose. Notice that the first x value is staying the same because that's the x value that I really care about. The actual point is x equals 2 and y equals 4. And then this is x2. They're also x values, and they are approaching the actual number that I care about. My next step is going to be to calculate the average rate of change on this interval. And you should remember that that means we're going to need 2 points. We're going to need to know the first point and the second point, which really means we need to calculate the y values. Go ahead and find the y values for each of these intervals. Perfect. So now we have 2 points, which means we're all set to use the slope equation. I'll go ahead and do that for the first one, and then we'll pause just to get the calculations done. y2 minus y1 is going to be 25 minus 4 over x2 minus x1 gives me 21 over 3, which turns out to be a slope of 7. Oops, up at the top. Go ahead and calculate the other ones. Estimate decimal values if you need to. Cool, so if you got the same calculations that I did, you should see that the slopes go from 7 to 6 to 5 as the intervals get closer and closer to the point at 2. Looking at the pattern, the numbers are decreasing. In fact, they're decreasing by 1 each time. So it seems reasonable to estimate that the slope, when we get all the way down to the point just at 2, should be something like approximately 4. And this is a really nice example, and I feel pretty good about that estimate, but it would be really nice if we didn't have to estimate. I wonder if there's a way to be exact about this process. Good news, there is. This is the formal definition of the slope of a tangent line. Right now, it probably looks like a whole bunch of gobbledygook. This is the most important definition you will encounter in all of calculus, although you may not know why for another couple months. Right now, pause the video to copy down both the diagram, including the little numbers, and the actual definition. When you press play, I'm going to talk about these pictures. As I talk, you need to somehow record the meaning behind each of these symbols. Maybe you do that in the left-hand column of your notes. I'll pause so you can copy first. Awesome. So you guys know how to read a limit by now. Just notice the variables for a second. We're basically saying m, which represents slope, in this case the slope of a tangent line, is equal to the answer of this limit problem. And this limit problem is talking about h getting closer and closer to 0. Notice that h is what's changing, which means that x is going to have to be a number that we know. You're not going to be able to solve this limit unless you know what x value you're talking about. H you don't have to know. H is the variable that's changing. Let me switch to the graph for a second. This is that familiar graph. We're looking for the blue tangent line at point P. And in this graph, they've labeled the coordinates of point P, this x value and this y value. X sub 0 is really just saying some particular x value. Imagine it being a number. F of x sub 0 means the y value that you get if you plug in that number. So there's your point. We want to know the tangent slope. Well, the strategy we used to estimate the tangent slope was to calculate the slope of a secant line. So they've calculated a secant line right here, and the secant line connects this point with this point right here. This is point Q. And what the notation is saying, and this is where you need to listen very carefully, the notation is saying that we're going to call point Q the point that is h units past x, x being the original point. So h in this situation represents the distance between the x value of the point we care about and the x value of the second point on the secant line. That's what h is. So x plus h is just the x value of this point, because you take this x value and you add the difference. F of x plus h is the y value of this point, because after we added the difference h, we take that x number and we plug it into the function to get the output right there. So this is a y value right here. Now, how do we calculate the slope between 2 points? Well, we do y2 minus y1. Look right here. That's what this is saying. y2 minus y1. And then we divide it by x2 minus x1. Well, what would happen if we take x plus h minus x? The x's would cancel out and we would just have h left on the bottom. This right here, the meaning of this limit is just the meaning of a slope of a secant line. We're taking the slope of a secant line. Now, what about the limit? Well, when we estimated a minute ago, we took this slope, and then we took this slope, and then we took this slope, and then this one. If I had to step back and describe what we were doing, I would say we were moving the second point closer and closer and closer to the first point. Using this notation, in order to move the 2 points closer together, we would just decrease h, because h is literally the distance along the x-axis between the 2 points. If we make this h value smaller and smaller and smaller and smaller, the points are going to get closer and closer and closer and closer. So why are we taking a limit? Because that's exactly what we just described. We described a situation where we're taking a number, making it smaller and smaller and smaller until it gets to 0. And then we're seeing what happens to the outputs of the slope function. Okay, if you've been paying attention, there have been actually 4 different ways to talk about the same thing. And I'm going to interrupt my own message with a public service announcement that you should open your textbook, go to page 90, and look at the bottom. The textbook describes them to you. It looks like this. Read this out loud to yourself right now. You need to understand what this means. 4 different ways to say the exact same thing. You should, in fact, memorize them. Okay, so armed with this new definition, let's go back to that example that we did just a minute ago. If you remember, we were looking at this function, and we had just estimated the slope that would be tangent to the point 2, 4. Well, instead of estimating, we came up with an estimate of 4. We can now calculate it precisely. The definition that you just saw said that the slope of a tangent line is equal to the limit as h approaches 0 of the difference quotient, and that's f of x plus h minus f of x over h. This is just a limit problem. Should be easy. Well, it's easy as long as you know what you're looking at. M means slope. H is some value that's getting closer and closer to 0. What's x? Right, this is the tricky part. In this situation, x represents the x value of the point at which we're interested in the tangent. In this case, we're interested in the point 2, 4. So x is just 2. In fact, I could rewrite the limit to look like this. In fact, notice that that means if I wanted the tangent at a different point, even if I had the same function, I would have a totally different limit. Well, in fact, that x is 2, so is this one. And actually, f of 2, I know what that is. That's just the y value when I plug in 2. Well, the y value is 4. So I can simplify this even further. Instead of f of 2, I just write 4. Now, f of 2 plus h, that's a little bit harder. What does this really mean? Well, function notation, this is saying we're going to take 2 plus h, and we're going to plug it into the rule for the function. The rule for the function is x squared. So that would just be, and again, don't drop your limit here, that would be 2 plus h squared, where I substitute this in for x. And then, of course, it's minus 4 that's over h. And now it's starting to look more like something that I know how to solve. This is just a limit. I can't plug h in right now because it would cause a 0 on the bottom. Well, what else could I try? No like terms, can't cancel the h. Maybe I could try foiling this out. It's, after all, it's just a binomial squared. If we write this out 2 times and FOIL it, here's what you'd get. And at this point, some of you might start to get excited because you can see where this is headed. What else can I try? I can try like terms. In fact, there are 2 like terms. This 4 and this negative 4 are going to cancel each other out. And we'll end up with the limit as h approaches 0 of 4h plus h squared over h. And oh, this is awesome. This is helpful because I can see that there's a GCF on the top. And if we factor out an h, we end up with 4 plus h in parentheses. H out front and h on the bottom. And those h's will cancel, and now we have a limit that we can solve. The limit as h approaches 0 of 4 plus h is just 4. And that's awesome news, not only because we found the slope, but because actually that means we estimated correctly last time. You should write your answer out as a sentence. Maybe your sentence sounds something like this. Notice that I said exactly 4. I'm kind of celebrating the fact that we have a real answer, also that we didn't have to do all those annoying secant line calculations. So I would like you to do a couple practice problems. This setting up this limit is a little bit tricky. The simplifying is almost always going to look pretty similar, but it's worth practicing a couple times because we have a test coming up. Unfortunately, there's very little time left in this video, so I'm going to stop, and we're going to do these 2 examples in the next video. Thanks for sticking with it.